Hello and welcome to the InSight pre-launch briefing. My name is Stephanie L. Smith. I am with the Media Relations Department of the Jet Propulsion Laboratory, which manages InSight for the agency. And we are here today for the historic InSight mission. We're going to get to know the mission, we're going to get to know some of the people behind the mission, and when I say historic, I mean it. This spacecraft will be the first to study the interior of Mars, the deep interior of Mars. It will also be the first West Coast interplanetary launch ever. So that's why we're all here today in the NASA hangar at Vandenberg Air Force Base with over 100 members of the media and credentialed social media to cover this mission. So we'll be taking questions in the House. We will also be taking questions from social media with the hashtag AskNASA. And for those reporters on the phone bridge, please press *1 to get in the queue. So before this mission takes off from the Golden State to the Red Planet, we're going to take a minute today to talk about the science goals, the instrumentation, and the launch logistics of InSight. So how does it all fit together? To give us an overview of what InSight will do and how it fits into NASA's overall plans for exploration, both Mars exploration and, more importantly, planetary exploration, we have NASA's chief scientist, Jim Green. Come on up, Jim. All right.
Thank you so much.
Great to see you.
Thank
All
you.
right, so tell these folks a little bit about what you do and what InSight will do.
Well, welcome to the pre-launch briefing, because this is really a fantastic mission. It's a planetary mission from the Discovery program. The Discovery program is all about doing first, getting to places that we've never been before, and this mission will probe the interior of another terrestrial planet, giving us an idea of the size of the core, the mantle, the crust, and our ability then to compare that with the Earth. This is of fundamental importance for us to understand the origin of our solar system and how it became the way it is today. In addition to fundamental planetary science, this mission I view as feed forward to human exploration on Mars. Now, we know that Mars quakes. We know that. We have seen avalanches from the Mars Reconnaissance Orbiter. Something has happened that has produced these kind of scenes. In addition to that, meteorites make it to the surface and impact it, causing quakes. So what is that rate? What are the Mars quakes all about? And this mission will take a good look at all those aspects. Now, for human exploration, here in California in particular, you know we need to be able to build the structures necessary to withstand the environments that we're in. This is a very quake-prone area of the country, but how quake-prone is Mars? That's a fundamental information that we need to know as humans then explore Mars. Now, everything in the solar system, these large planets that are put together, are still cooling off, and that includes Mars. The heat probe will go down and measure that temperature difference. That temperature difference could be large, could be small, but it's an important part of knowledge of how this planet is evolving. And can it give us information about how we might use that heat differential to heat a habitat? We know the temperature on Mars in one day, 170 degrees Fahrenheit change in one day. And we have to be able, as humans, living on Mars, working on Mars, to survive that. So how can our resources that we discover on Mars enable that? So this mission does so many fundamental things, not only in planetary science, but in human exploration. And it's a very popular mission. How popular? Well, we asked people if they'd like to add their name to a chip. Here's one of the chips. This is what it looks like. And the response was unbelievable. 2.4 million names are on this chip. And it is affixed to the surface of the spacecraft. How cool is that? So I hope you're one of them. It's too late to put your name on this one. It's already in the fairing, ready to go. and Saturday we're going to launch it. That's the plan. So with that, may I take a question or two?
Absolutely can. And if you didn't get your name on InSight, you'll probably be able to get your name on Mars 2020. So file that away. But let's go ahead and take some questions from him here in the house. Any questions for Jim?
That's because I answered
We
them
do
all
have a
earlier
reporter
today, I
on the
guess.
phone line. Okay, let's go ahead and go to the phones then. If we have a phone connection, please state your name and affiliation.
Elizabeth Howell, Space.com.
Go ahead.
Okay, thank you. Mr. Green, I would like to know if you could talk a bit about the decision process back in December 2015 after the leak occurred on Mars InSight. If you could talk about the decision process to actually keep the mission going at that time as opposed to stopping it, which was one of the things that was being considered. Could you let us know just how that decision was made and how you decided to actually go forward?
All right, so what the question is really all about is planetary windows. When we select a mission to be completed, we have in mind that it is going in a particular window. Planetary windows are a blessing. That means we have to get our mission together to be able to launch it, but it's also a curse. Okay, and so when not everything is together, when not everything is working well, and we miss that window, we have to wait for the next one. So for Mars, for everything to line up again that allows us to launch to Mars, that window is every 26 months, okay? So our window starts this Saturday, May 5th, and will go till June 8th. That's it. If we can't launch InSight then, we wait 26 months. But indeed, the previous window that we were planning to launch InSight, we couldn't get it all together. That actually happens every once in a while. You know, this business is tough. You know, these are one-of-a-kind missions. They're making extraordinarily important observations, and indeed, the scientific basis of this mission and its importance that feeds forward not only in planetary science but in human exploration was a factor in the decision to keep things going, to complete the instrumentation and get it ready for launch. And that enables us right now to be in the position we are in, with a spacecraft sitting on top of an Atlas, ready to go to Mars, and everything is in top shape.
All right, well, thank you so much, Jim.
My pleasure. Thank you.
So you probably may have noticed by now that there is a full-scale mock-up of the InSight lander in our set today. To talk a little bit more about the design, build, and spacecraft health of the actual flight hardware, which is tucked up inside of its payload fairing right now, please welcome to the stage Tom Hoffman, the InSight project manager from JPL, and Stu Spath, the InSight program manager from Lockheed Martin Space. Come on up, guys.
Thank you, Stephanie.
I will give you the floor.
Thank you, Stephanie. What you see in front of here is the fully deployed spacecraft. So we have the solar arrays, you have the lander legs, all as it will be on the surface. I'm going to explain in just a minute about how this is on the rocket right now. But before I do that, I just want to say I'm really, really excited. I'm going to Mars. I hope you guys are excited too. Are you guys excited to be going to Mars? Come on. All right. All right. This has been a labor of love for me for 7 years. I've been on this project since the very beginning. We've worked really hard to get to this point. I can't describe to you in words how very excited I am to see us at this point ready to go off to Mars, ready to send this to another planet. It's going to be awesome. So like I said, this is what we look like once we get deployed, fully ready to take our science on Mars. But before that, we start out a little bit different. So right now on the rocket, we actually have these solar arrays are all folded up underneath the deck. These legs here are all tucked up here, so it's very compact. And in fact, we have an aeroshell around this, which consists of a heat shield and a back shell. And in fact, we even have a cruise stage on top of that as well. So we have all of that. That's what's in the rocket right now, ready to go to Mars. So one of the cool things for me, being a native Californian, is this is the first time ever we're doing an interplanetary launch from the West Coast. So we're finally breaking the monopoly that the East Coast have had, the Floridians have had on interplanetary launches. So it's exciting for me as a native Californian to have that opportunity. So what I'd like to do now is play a video for you, and what that's going to show you is what the launch is going to look like. Hopefully it's as clear as this video shows it to be in a couple of days. So we're all tucked up in this. We launch, and so one of the cool things, if you are in Southern California and you're an insomniac or you just get up really early at 4:05 on Saturday, you'll be able to see this from your backyard. So this expanding circle actually shows you what the viewage is. So pretty much anywhere from Central California, from this area all the way down to Mexico, you should get pretty good view of the spacecraft at that time. It's going to be the brightest object in the sky. It should be quite spectacular. So, you know, set your alarms, get up and watch this if you don't happen to be here at Vandenberg. So once we get that launch off, we still have to get to Mars. So we have a 6.5-month cruise. During that time, we do what we call trajectory correction maneuvers. We do a series of those, and what those do is it allows us to actually land on the surface of Mars on November 26th of this year, which is Cyber Monday. So again, if you don't have, you know, if you're shopping online, you know, you're doing your holiday shopping, whatever, and you want to see something else, you can put that on your other screen. If you're at work, of course, you're not doing that, right? You're maybe doing that on your personal computer. But put that on, and you can see us land. We're going to land about noon on the 26th of November, so Pacific time. So that's going to be really cool. So once we get there, we have to go through what we call entry, descent, and landing phase. So that's where we start off at 12,500 miles per hour, and within 6.5 minutes, we get down to 5 miles per hour when we land. So I have a video to show you that kind of describes that process. So you can see we're coming in very hot. Literally, we use this aeroshell to take the heat off. We're still going at supersonic speeds when we pop out the parachute. That slows us down even more. Once we get down to a good speed, we drop off that heat shield. You can see the exposed spacecraft there, and then we start acquiring the ground with our radar. That's telling us what our velocity is. When we get down to the right velocity, we let go, and actually the spacecraft free falls for a while. Then it uses the retro rockets to slow it down to 5 miles an hour with the legs popped out in this configuration. So that gets us down to the surface, but that's not the end of it. As I said, it doesn't look quite like this right away. We actually have to take these solar arrays and deploy them. Stu is going to talk a little bit more about that in a minute, about what we do. But then the next step is we have to actually deploy these elements, the instruments, from the deck to the ground. It's basically a second entry, descent, and landing for us. So we're about a meter or so, 3 feet from the ground, but we got to get that last little bit. And that actually is going to take us a little bit of time. It seems like that should be pretty simple, but actually what we're going to do, once we land, we're going to take some pictures of what the terrain looks like. And at JPL, we actually have a test bed. We're going to reproduce that terrain exactly in that test bed, and then we're going to practice deploying each of the instruments over and over and over again to make sure that we get it right, exactly right. So that's going to take us about 2 months, roughly, to get the instruments from the deck down to the ground. I wish it was about 5 minutes. But I actually have a video that goes really, really fast, and I really wish it went this fast. So if we show the next video, it gives you an idea of what that deployment process is. So you can see the solar arrays are already deployed. We're putting the seismometer down first. We do that first. That's what this is over here. And then we take the wind and thermal shield, this white wok-looking object. We place it over top of it, and that basically insulates it from the environment as well as we can on Mars. And that's what's going on right now. And then once those are deployed and checked out and everything's looking good, then we take off the heat flow physical properties package and we put that down next. So that whole process, I wish it went as fast as this video. It'd make my life a lot better. My hair would be a different shade of blonde than it is now. But it doesn't quite work that fast. So we get down to that point, and then now we're actually set for the scientists to start getting the science that they want, the whole reason behind this mission. And you're going to hear a lot more about that in just a little bit. But before I get on to that, I did want to say it's really, this is really an international collaboration. There's people from all over the world. It really takes you've heard it takes a village to get something done. In this case, it takes villages across the globe to make this happen. So we have instruments from our international partners. Most importantly, we actually have our spacecraft is being built by Lockheed Martin in Denver, and it's my pleasure to introduce Stu Spath to tell you more about that. And one thing, it's kind of just a personal thing with Stu and I, this is a second mission that we've worked together. So we've been both on this mission for 7 years. Together we've been over 10 years. We worked the previous Discovery mission, Grail, which was a mission to the moon, gravity mapping. So it's great to be able to work with Stu Spath again. So,
all right. Thank you very much, Tom. Appreciate it. So because Lockheed Martin has worked on 20 previous Mars missions, someone actually asked me recently, do I consider this InSight mission routine? And I'll steal a little bit from Tom Hanks here in Apollo 13, a slight rewording. There's nothing routine about going to Mars, especially landing on Mars. I mean, this is a tough mission, and we're happy to be a part of it. As Tom mentioned, I've been on the program from cradle to grave for about 7 years now, and I can personally attest that on Saturday morning, the anticipation and the excitement is going to be second to none. So I'm really looking forward to getting this thing off the ground. Let's talk a little bit about what Lockheed Martin's role was. Tom alluded to it a little bit. Basically, the 3 phases that we participate in are the design and development of the spacecraft components, the integration and test phase, and then the flight operations. So for the design and development, those of you that have been involved in the Mars program for quite some time or covering it, you'll probably notice this looks a lot like Phoenix lander, which launched in 2007. And that's intentional. One of our strategies is to build on our previous successes so that we're minimizing the risk and maintaining the risk posture that we want to on these missions. So some of the things that are inherited directly from Phoenix are the basic structural layout of the lander here, the 3 legs that deploy during the descent and landing phase. You can see the descent thrusters underneath here and the fuel tank. The entire prop subsystem, propulsion subsystem is pretty much the same as Phoenix. However, there are quite a few things that are different from Phoenix. Inside the interior of the lander, which you can't see from this view, are the flight electronics, the avionics, power components, and the flight computer. Those are all inherited from MAVEN, the Mars orbiter that launched in 2013. So we have modernized the electronics since the Phoenix era. Another thing of interest here is this mission, unlike Phoenix, has an X-band telecommunication system. And this is the Mars, this is the medium gain antenna here that goes direct to Earth with a radio science beacon. And the purpose of that is actually as a science investigation. Bruce will talk about this during the science. But it's one of the cases where the spacecraft component actually doubles as a science investigation. The second phase that we get involved in is the integration and test. As the components come in, we have to assemble the flight system and test it so it's ready for the rigors of space. So if we could roll the integration video. All of this video was filmed in the Denver High Bay facilities. Here you see the lander early on in a hang-down mode. We're installing the components. This is the cruise stage, which gets us to the planet, not shown here on this stage. This is early on, the science deck, before any of the components had been installed, but we're doing the propulsion integration testing there. Here is our thermal vac chamber here, and you can see it's a long, deep chamber. The InSight lander is being lowered in there, and then it spends about 2 weeks in this thermal vac test to make sure we can survive the rigors, the thermal extremes. Jim talked about the big swings from night to day. This video here is obviously the solar arrays being deployed. One of the first things we do after we touch down about 15 minutes later is deploy the 2 solar arrays. And so you can see this was the final test we did in Denver before packing up the arrays and stowing them. And then this is the final operation in Denver. The yellowish component is the heat shield that gets installed over the top of the back shell, and then it gets put into the shipping container and flown out here to Vandenberg via a C-17 flight. Finally, I'll talk about flight operations. From the moment this lifts off on Saturday to the end of the mission, the spacecraft team will be participating from Denver in our mission support area, doing the commanding and telemetry monitoring and so forth. And so we'll be involved in the mission, the spacecraft elements from the entire launch period all the way to the end of mission. So I want to wrap up by saying thank you. A big shout out to all the hundreds of men and women at Lockheed Martin that made this happen. It was not an easy task. I wanted to say thank you to JPL for allowing Lockheed Martin to be part of the team. And I just wanted to say it's going to be a great mission. We're proud to be a part of it, and we are go for launch.
All right. And with that, we're going to open it up for questions. Anybody have any questions about engineering, spacecraft, instrumentation? If you have a question, please raise your hand and wait for a microphone runner to get to you. Can we get one right down here? There we go. State your name and affiliation.
Hi, Eddie Irizarry, Air Sky. Is it better or easier to go to Mars from polar orbit, and why?
It's actually we're going to end up doing one orbit, like a polar orbit, and then we're going to make a left turn on our way to Mars. So we're essentially going to be getting out at the same trajectory as if we launched from Kennedy Space Center, because there's a big advantage of getting out near the equator. It's just we're not very close to the equator here, obviously, and so we need to get there. We do that with an orbit around the Earth and then a left turn.
Okay. We'll take another media question here.
Marie Langer, the Swiss daily NZZ. Could you elaborate a little bit on for how long you think you will be able to receive data from Mars now?
Yeah, so this mission is designed to last 1 Mars year, so that's 26 Earth months. But there's nothing that's life-limiting on the system, so hopefully we'll last a lot longer than that, but at least 1 Mars year is our plan.
Okay, it looks like we've got some social media questions on this side of the house. There, Shannon, if you can go to the front row.
Hi, my name is Maddie Garcia. I'm from MIT, representing MIT students right now. I actually have a question for you about the thrusters. After speaking with the Lockheed Martin representative earlier, I learned that there are no redundant thrusters. With such a high risk, I guess, maneuver, like having like a propulsive landing, how do you account for that risk? Like, how do you justify not having any backup thrusters?
Go ahead. I'll field that one. Yeah, so again, because this is so high heritage in the propulsion system from Phoenix, we don't consider a high risk there. We can actually tolerate some outage there, but the main components of the thruster, the reason we do the propulsive landing is because Phoenix did it, and almost 40 years before that, Viking did it. So obviously, the airbags have been used, or the sky crane on Curiosity, but the propulsive landing is the technique that we've used at Lockheed Martin, and we feel like it's flight-proven, ready to go.
Okay, we have a reporter on the phone lines, Aerospace America. Go ahead.
Tom Rise with Aerospace America. Thank you. NASA InSight will dig deeper into Mars than humans have ever dug on another world. It'll use that self-driving spike to drive the heat probe into the ground. Are there any contingency plans you have in case the ground is tougher to dig than you anticipate?
Yeah, actually, this is going to be a good question to ask Tillman Spahn when he's up, but we've done a tremendous amount of testing. We feel very confident that we're going to a location on Mars where we will successfully penetrate. And even if we do hit some rocks, as long as they're not big flat rocks, we have a really reasonably good chance of getting past those and getting down to the depth that we want, which is about 10 feet. That's a requirement. The goal is about 16 feet. But Tillman's going to talk a lot more about the heat flow physical properties package coming up in the next section.
Okay, we have another question on the phone lines. Reuters, go ahead. Reuters, can you hear us?
Oh, I'm sorry. Hi. Thanks for taking my call. I just want to ask, how many missions have there been to Mars, either up till now, at least for the U.S. space program, either by way of landers, orbiters, and rovers? Does anybody know?
I think the answer is 21 U.S. missions.
Does that sound right, Dennis?
Sounds about right.
Okay. We're going to go with 21.
We will get that number for you after the show. Okay. Well, thanks very much, guys. Big round of applause for Tim and Stu.
Thank you.
And engineering of InSight. Okay, right this way. So at 4.5 billion years old and not one visit to the doctor, I think we can all agree that Mars is overdue for a checkup. So InSight will be checking the pulse, the reflexes, and the temperature of the planet. And to tell us more about those science goals, please welcome to the stage Bruce Banerdt, the InSight principal investigator from NASA's Jet Propulsion Laboratory. And after he says a few remarks, we're also going to have some other key members of the science team. Annick Sylvestre-Baron, the Deputy Project Manager of SEIS from CNES. Philippe Lognonné, the SEIS Investigation Lead from IPGP. And Tilman Spohn, the HP Cubed Investigation Lead from DLR. But we're gonna start with you, Bruce. Okay. So Bruce, how long have you been working to put a seismometer on the surface of this planet, of Mars?
Well, Thomas Seuss talked about being around from the inception, from the cradle. I guess I was there on the first date. So I've been actually, before there was a spacecraft, before there were even instruments, there's the scientific questions. And those scientific questions have been around really since the beginning of the planetary exploration. And those questions are something that intrigued me when I was in graduate school. And finally, kind of in the late 80s, early 90s, I started working on planetary seismometers, planetary seismic missions. And then this particular mission really started coming in, coming into play, ideas were coming together in the early 2000s. So I've been working on this, like I said, more than 25 years. And you can imagine just how incredibly exciting it is for me to be here today. Not 25 years, not 2 years, not even 2 days away from launching to Mars. So this is really amazing. And the science that we want to do with this mission, the reason we're going to Mars, is really a science of understanding the early solar system, how planets form, how rocky planets form. And the way we can do this is by using the fact that the terrestrial planets, the rocky planets, all have certain similarities. They all formed in basically the same ways. And today we know that Mars, Venus, the Earth, Mercury all have kind of the same basic structure. They have a very dense, heavy iron nickel core. They have a rocky mantle made of relatively dense silicate rocks. Not the kind you see on the surface, but rocks that have been kind of pushed together, the atoms kind of squeezed together a little bit more compactly. And then a crust of lighter rocks, the kind of rocks that you can actually pick up, throw at people, whatever you want to do with them. These are a little bit different than the rocks that make up the bulk of the planet. And yet, the planets all form from the same kind of stuff. They all form from carbonaceous chondrite, meteorites, some cometary stuff thrown in. And somehow we ended up with planets that are made of very, very different kinds of rocks, very complex structures. And that process that we know sort of generally how that works is called differentiation. When the planets first form, they melt, either completely or partially, and then they start to separate. The heavy stuff sinks to the bottom, the light stuff floats to the top, and that process sounds relatively simple, but what happens, of course, is that it starts getting mixed up, and we don't really know exactly how that works. And so we want to understand where the Earth came from, where the planet that we lived on, how it came to be the way it is today, and we start looking at Earth's history, and we run into a brick wall because the Earth is so active that the evidence of all those processes has gotten basically erased by plate tectonics, by vigorous mantle convection, and people say, oh, that sounds dangerous. Well, by vigorous, we're talking about millimeters per year kind of motions, which for a geologist is like, whoa, get out of the way. But the Earth really doesn't have that evidence anymore. We went to the moon, and the moon has lots of evidence left over. It froze itself pretty early on in its history, but it's so small that the pressures and temperatures inside are only characteristic of the Earth down to maybe 100, 150 miles or so. And so the vast bulk of the Earth's interior underwent processes that never ever happened on the moon. So Mars is kind of a unique opportunity. We call it the Goldilocks planet. It's not too big, it's not too small, it's just right. Okay, so it's actually undergone the processes of planetary differentiation that the Earth did, but about maybe 20, 50 million years after it was formed, it just kind of stopped, and we have lots of geology going on the surface, but all those fingerprints of those early processes are still still retained in the deep interior. And so that's why we want to go measure the fundamental parameters of the deep interior. The thickness of that crust, which gives us sort of the amount of scum, if you will, that floated to the surface, the size and the density of the core, which tells us how much iron sunk down to the center, and not only how much iron is there, but how much other elements were sort of brought with it, because we think it's not pure iron, because if it was pure iron, it would be frozen solid today. But since we have other things mixed in, it actually allows the core to stay molten. It lowers the melting temperature, just like when you throw salt on a frozen sidewalk, it melts the water on the sidewalk. And so we want to know, what the composition of the core is, what its size is, and finally what the structure of the mantle is, and the dynamics, which is related to the amount of energy involved, which is related to the temperature. And so we do that with sort of 3 basic investigations. The first is the seismometer. This is really the heart of the InSight mission. The seismometer is what allows us to see deep into the planet, to have insight into the planet. And it uses the seismic waves that are generated by Mars quakes. And seismic waves are just vibrations. And if you live in California, you're very familiar with these kinds of vibrations. But it's not actually going to measure things that are going to shake the spacecraft around. It's measuring very small vibrations that started on the other side of the planet, traveled all the way through, and then come back up to the surface underneath the spacecraft. And those vibrations, by the time they get to InSight, they're very, very small. And we do this on the Earth more or less routinely. Here in California, we pick up earthquakes in Japan. We pick up earthquakes from the middle of the ocean, from Europe, all over the place, many, many times a day. And that's considered pretty routine. It's not quite so routine on Mars, because what we're trying to measure are vibrations that are so small they're kind of on the scale of an atom. The resolution limit of our seismometer, sitting in the dirt on Mars in the weather, is about 1/2 the radius of a hydrogen atom. So it's a very, very exquisitely precise measurement. And so we have our seismometer. We put the windshield over it to keep the wind from blowing it around. We have other sensors on here to keep track of the weather, keep track of magnetic field variations, all the things that can sort of creep into our data so that we can understand what are seismic waves and what aren't. And then when we get those seismic waves, it turns out as they travel through the planet, they actually pick up information along the way. When they travel through rocks, different rocks affect the waves in different ways. And so when they come back up, all those little wiggles you see on seismograms sometimes after an earthquake, scientists understand how to take the shapes of those wiggles, their frequency, their amplitude, polarization, the timing, all kinds of properties of those waves, and pull that information out that the waves have kind of picked up along their path. And finally, after we've gotten many, many Marsquakes from different directions, we can put together a 3-dimensional view of the inside of Mars. Our second instrument is the heat flow and physical properties package. And this is the mole that goes down deep into the Martian crust. Actually, not deep into the Martian crust, into the Martian soil, about 5 meters or 16 feet. And it measures not just the temperature down there, but it measures the temperature all the way along the hole that had gone down. The instrument is actually not the mole that pulls it down. That's just the truck that gets it there. The instrument is actually the cable that it pulls behind it. And Tillman will tell us a lot more about that later. But basically, it allows us to understand the heat budget of the planet, the energy budget that is driving the geology, that's driven the evolution of the planet for the last 4.5 billion years. And finally, we have our radio science experiment, which we call RISE. And that's actually not an instrument, but it's the radio transmitter on the spacecraft. It has a couple of antennas, these little conical things here. They look at the morning and the evening horizon as the Earth rises and sets, and it communicates directly with the Deep Space Network stations here on Earth, those big dishes out in the desert, which transmit a radio wave up to the spacecraft. When we receive it here, we have a transceiver that turns that signal around and sends it right straight back down to Earth without even a break in the signal. It's vibrating at, 3 or 5 gigahertz or something like that, and we don't even break that wave. It comes back down, and by analyzing the Doppler shift in that signal and the timing of that signal, we can track the location of the spacecraft at Mars, 60 million, 100 million miles away, with an accuracy of something around a foot or so, maybe a little bit less, which is as to me, that's as close as you can get to magic and still be science, that you can actually make those kinds of determinations. We track it during the day, and as the planet rotates, it goes through a little bit of an arc. We can then figure out where the North Pole of Mars is pointing to a really high degree of accuracy, and over the course of the year, we can watch that North Pole wobble just a little bit because of the core sloshing around inside the planet, and that will give us a very, very tight constraint on the size of that core and its density, and so its composition. And so that tells us the structure of Mars. The structure of Mars tells us something about the processes that put that structure together. We can put those into our models, extrapolate it to the Earth, and understand how the Earth formed 4.5 billion years ago. And that's really the crux of the science behind this mission.
Well, much like InSight inside of its payload fairing, we're jam-packing a lot of awesome into a very small space and time this afternoon. And I want to make sure that we get a couple minutes with each of our science team key members here. So let's turn it over to Annick. You want to say a few words?
Good afternoon, ladies and gentlemen. So I am Annick Sylvestre-Baron, the deputy of the SES project manager, who is Philippe Lognonné. What a great achievement today to be all together close to the launch. And I'm very proud to represent the French Space Agency and the SES teams, the SES engineering teams. So I just want today shortly to focus on two challenges we succeeded. The first one is for a French agency to coordinate 5 countries, including NASA, GPL, the United States, and the other countries. The Germany provide for us the leveling system. The Great Britain funds and provide a seismometer called Shock Period. They are free on this amazing instrument. And the Switzerland provides the electronic box. The electronic box is inside the lander. You can see it. So concerning the French Space Agency funds the VAFB, the other seismometer, and also provide all the system engineering. And we integrate this incredible instrument and perform all the tests required by NASA. Can I have some picture, please? So another challenge we faced and succeed is to validate all the functional and performance tests. For them to simulate the gravity on Mars, we have to tilt our seismometer up to 68 degrees to have our seismometer operated. So at ambient, it's easy to have a goniometer to do it, and to be able to validate at cold, because you know on Mars the temperature could be very, very cold. You could see on the picture that in our thermal chamber we have our smart INT team built is the other one. The first one, please. We can see the huge mechanical GSE, what we call, to be able to tilt our instruments. We also performed a test, a final test in beginning of this year. It was a great achievement for our teams, and as you can see in the corner, you can see Bruce and Philippe attending a test in Black Forest. It was an old silver mine, and with our qualification model, with representative seismometer, we can validate the performance requirement, and we can say today that we reach the required requirements. So we are very proud for that. And finally, we participate also to the test in Lockheed Martin, and it was very interesting, instructive for all the teams to participate to this test. So for the 5 countries, it's around 260 people women and men, engineers, who participate to this challenge and to have it ready to launch on Saturday. So I really thank NASA and JPL to have trusted us since the beginning. It was a very wonderful adventure, a space adventure like we like it. And for you, for all the team, it was very fruitful to share our multicultural way to work. Thanks.
Thank you so much, Annick. All right.
Okay,
so we just got a couple minutes here.
Hello, so I am Philippe Lognonné. I am the lead investigator of the Seismometer. With the first slide, so I will continue to thank NASA, JPL, and especially all the technical team, you know, in the world, you know, in many places, and of course all the space agency who made this mission possible. So InSight, and for seismology, it will really be a piece of history, a new page of history. Why? So we started seismology on the Earth 130 years ago. We started seismology on the moon 50 years ago, and we will start seismology tomorrow by launching the mission. So it's really a new planet where we discover something. Now, the key point is Jim Green and Bruce Banerdt told you a lot of seismology, but I want to convince you that we can detect the inside of something with seismology. So please give me Mars. You know, this is one Mars.
Anything you
want.
And
I will ask you a question, you know. Okay, what is inside this planet? I make an impact like this. So tell me if this is full or if there is nothing, you know. I guess you know immediately the answer because you got the sound of the planet, and the sound is wave. You know, it's almost like seismic wave, and I was making an impact with my hand. So therefore, you immediately get that there is nothing inside, and we will do the same thing on Mars with impact with quake, and of course, we will find that there is a lot of stuff inside. Now, I have a movie for you because, give me Mars back, please. No, okay. I am not finished. So now, this is a quake. You know, we have one lander, and we need to detect a wave and to measure the speed. So therefore, the point is that we will have a quake, you know, the wave turn around the planet. And the nice thing is that we know exactly what is the distance of the planet. This is a circumference, so therefore when we catch the wave 2 times, first time when it is arriving first, and the second time when the wave has made a full turn, you know, it is like in a stadium, you get immediately the speed of the wave, and this tells you everything from the inside. Now, you see on the movie, the big problem is that, okay, this small dot at the end, you know, is the wave after a full turn. You see that it is something like 10 times smaller than the big wave because it's a lot of, you know, distance to go through. So therefore, give me the next slide, and I am done with Mars because I know the interior now. So now I need to detect that a very small signal of the size of the atom, you know, and therefore the sensor inside must be protected against temperature, against wind, you know. So therefore, next slide, you get all the protection. So you have this evacuated sphere, you have the thermal protection. And next slide, you know, this is what you see here, but on the top of that, we will put the windshield to protect last time the seismometer. So this is almost like a portable seismic vault we will carry on Mars, not the gold mine or you know, we have used, but this is something we go on Mars. Okay, next one. Now we need to deploy that, and you need to see that for the first time, and this is the next time, next slide, and the last one. So next, yes. So for the first time, we will deploy something with a robot on the surface of the planet. This was made on the moon by an astronaut, you know, by many astronauts on Apollo 11, 12, 14, 15, 16, 17. And here, you know, we have the robot, but we have the arm of the robot, we have the haze of the robot, and that guy, you know, will do the job for us so to deploy the seismometer on the planet. Now, seismology is not the only thing we want to do. We also want to do heat flow, and I will give the floor to my colleague, Tilman.
Thank you very much, Philippe. Interior structure is important, but planets are engines that use the internal heat to do geology on the surface, as everybody in California should know. You can see it all over the place. I'm Tilman Spohn from the German Aerospace Center, DLR, and I spent most of my scientific career studying the internal heat of planets. And now, thanks to this mission and all the wonderful people that are involved in here, I have a chance of measuring characterizing Mars as an engine, just as a thermal engineer would do that would use the heat radiating from the motor to study the pace at which the motor is running. And that is what we're doing when we measure the heat flow from the interior of Mars. Now, how are we going to do this? This is our experiment, the heat flow and physical properties package. It has a tower here in which we have a probe that hammers itself into the ground, and a compartment in which we have a tether that is equipped with very sensitive temperature sensors that it carries behind it, and that will measure the temperature. Now, I have a video to show you how this all works. Can we have the video? Here we see the mole in the tower, and to the left we see the hammer. You see that a hammer is pulled up and is hammering onto the anvil, and it is driven by a spring that is compressed as the motor drives the hammer up. Now, we're not going down at once, but we're stopping every 2 feet or so to take a measurement of the thermal conductivity of the soil. We do that by heating the mole and measure the temperature of the mole itself as a measure of the heat escaping from the mole. We'll do this 10 times until we reach the final depths of 16 feet, and then we switch on the temperature sensors and record the temperature over depth and time for up to 2 years. Now, taking the temperature gradient, or the rate at which the temperature increases, times the thermal conductivity that we measured, gives us the heat flow. Very simple, very straightforward, but as in planetary science so often is, very difficult. The devil is in the details. Thank you very much, and I'm ready to take questions.
All right, so we've got time for, you can hang on to that. We've got time for just a couple of questions here in the house. Let's get a microphone over here, and then on deck, a microphone on this side. Go ahead.
Hi, Don Haladiak with the Canadian Broadcasting Corporation. My question is regarding the seismometer. Normally it's put on like a bedrock or something more firm. Here you're just placing it right on loose regolith, right on the surface of Mars. How confident are you to get good results?
Okay. So we made a lot of model in order to be confident, and on the top of that, most of the time you have to see that the problem, what you call is seismic coupling. The problem is not the fact that the waves are not able to go through. The problem is that the seismometer is able to move a little bit. So therefore, this is why we cover the seismometer with a shield. And here, you see, we have a system which will release the tension of the cable to the seismometer. So therefore, we have made the model, we have made tests, and we are very confident to meet the requirement with all that stuff.
Okay, and we had one question on this side of the house.
Hi, I'm wondering if the heat flow probe will be able to tell us information about the ice below the surface on Mars, and if that will help us with drilling for water in future manned missions.
Okay. Bruce, do you want to take a crack at that? And then for future missions, we'll turn over to NASA headquarters.
Okay, so the place where InSight is landing is just really close to the equator of Mars. So all of our calculations of the stability of ice indicate that we don't expect ice to be present below InSight. Seismically, it's possible to detect ice, although our particular experiment isn't really optimized for that kind of detection. If there was a very thick layer of ice, and by thick I mean, fractions of a mile, not many feet, that would probably affect the seismic waves and allow us to sort of tease that information out of the data. But we really don't expect to have that as a component of this particular mission because of the location that we're going to.
We could see it in the thermal conductivity.
All right. Okay, we've got a question on the phone lines from Irish Television. Go ahead.
Thanks very much. From Dublin, the home of the man who invented seismology, Robert Mallet. I have a question. I'm sorry, but this new format has thrown me a little bit. If I may ask the engineers and Mr. Green or Dr. Green a question, and that is, what again, going back to the first question at this session, what happened with the seismometer that caused a 2-year delay? And for Dr. Green, did NASA at some stage consider canceling this mission as a result?
I can probably actually answer.
Okay. Yeah. So Dr. Green is no longer in the House. Bruce.
I was very involved in both those processes. So the thing that caused us to delay the launch in 2015 was a problem with the seismometer. The seismometers are kept in a very hard vacuum inside a spherical cavity, and but you need to be able to get the signals in and out and the power in and out through that cavity. And so we have what we call feed-throughs. And one of those feed-throughs was not capable of maintaining itself under the large temperature extremes. So when we actually tested it at Mars conditions, going down minus 100 degrees, 120 degrees Celsius, it developed a very tiny crack and started leaking, started allowing some air to come in. And it's a very small leak. I calculated once that if you had a leak in your tire, it would take about 50 years to see a 1 psi difference. But this was enough to sort of upset the whole apple cart in terms of the sensitivity of the seismometer. We tried to fix it. We had a very limited amount of time. But again, the kinds of things that we were trying to use to patch it, again, had to be able to withstand these huge temperature extremes. And we finally realized that we were not going to be able to do a confident job of patching this, that we would absolutely be certain that it was going to work on Mars, and we decided that it was much more prudent to stop and not send something to Mars that we were unsure of, but step back and see whether we could do something about it. So we went to NASA a few months later with a plan for fixing this, and we had I think we put together a very solid plan for showing that we could fix it, that we could fix it in plenty of time, that we could test it to the level that we would not have any doubt about it once we got to the spacecraft. And between the solidity of that plan, and as Jim said, the importance of the science that this mission was going to return, NASA made a decision to allow us to go forward. They watched us very carefully, as you can imagine. They watched the progress of the seismometer to make sure that we were actually meeting the milestones for, we actually went and redesigned that vacuum system to make sure that it not only was as good as it was supposed to be before, but it had extra margin, extra ability to maintain this vacuum. And so I hope that answers your question.
All right, and with that, a round of applause for our science panel. Right this way. Okay, we're here for a launch, and to tell us more about the Atlas V 401 that will be InSight's ride to space, please welcome to the stage two of NASA's steely-eyed missile men, Tim Dunn, Launch Director of NASA's Launch Services Program, and Scott Messer, the ULA, NASA LSP, and Delta II Program Manager from KSC. Gentlemen.
All right. Thank you, Stephanie. All right, so Tom brought this up earlier. Who is excited? Excitement over here? All right. I know where the social media folks are, so I'm going to focus on you guys. These professional media guys, it takes a lot to get them excited. Wow. I mean, that rocket over there, this amazing spacecraft, we got it all bundled up together. It's just about 2 miles from here, south, up on the hill, Vandenberg Air Force Base. I live in Florida. I get to come to California, and for the first time ever, launch a mission to Mars. What's not to be excited about? I mean, this is thrilling. And what's amazing is occasionally, the steely-eyed rocket scientists talk, and it takes a lot to get us excited. But you can sense within the launch team, all aspects of our launch team, JPL, NASA at KSC, our resident office here, our Air Force team, the 30th Space Wing, and even, this takes a lot to get folks in Washington, D.C. NASA headquarters is even excited, right, Dennis?
Right there.
All right. So as Stephanie said, I'm Tim Dunn, and I am absolutely humbled and honored to be the launch director for this mission. And I stand before you, and I just represent a huge organization called NASA Launch Services Program. And LSP takes care of you, the taxpayer. How do we do that? We match up requirements like this beautiful spacecraft that needs to go to Mars with those rockets like the mighty Atlas V. So what we do is we compete those requirements across the launch industry, SpaceX, Orbital ATK, and in this case, United Launch Alliance. And that gold standard rocket that you see a model of, that is an incredible, incredible capability that we have. And I'm just thrilled to be part of this team. So I just want to take just a moment to tell you kind of where we've come from in the recent history and what's going to happen less than 2 days from now. So let's look at some video here. Okay, there's the mighty Atlas first stage on its way out to Space Launch Complex 3 up on the hill here on South Vandenberg. That's a quick sequence of the erection going into the launch mount there at Slick 3. Okay, that is the ISA transition structure that takes us from the first stage down to the second stage, and here is the second stage of an Atlas V. This is called Centaur. It's got an RL-10 engine on it, an incredible performing space vehicle. So there's your second stage of an Atlas V. Going up, we erected the first and second stage back in March, so just under 2 months ago, we were putting it all together. So here you can see the professionals from United Launch Alliance doing that mate. And that's what it's all about right there. That's the spacecraft InSight encapsulated in the metal fairing, the 4-meter fairing being erected. A little bit of a foggy day. This was Monday, the 23rd of April. And there we are in the MST. Beautiful shot of some of the artwork there on the side of the payload fairing. All right, so there's my video. So that's what the rocket looks like inside the mobile service tower. So what have we been doing just this week? We did a flight readiness review on Monday. We did a mission dress rehearsal on Tuesday. The entire launch team, all agencies, we are primed and ready. And just this morning, we did the launch readiness review. And we got goes from all aspects, all organizations that have a vested interest in launching InSight. And so we are go for launch. Yes, we are. So moving forward, tomorrow is Friday, so may the 4th be with you. And so what I told the launch team was, may the 4th be with you during your crew sync day and your crew rest day, because we're all going to get rested up during the day because it's an overnight launch. 4:05 a.m. is our T0. That's a tough one for the launch team because you're working all night. Hard to go to sleep tomorrow, but we're going to try to get some rest. Very exciting mission. So then we got to get in on console. We're going to move that mobile service tower that surrounds the Atlas V right now. Back that away. That's going to happen about midnight tomorrow night, first thing Saturday morning. Then we're going to put all of the cryogenic propellants, the liquid oxygen, liquid hydrogen on board. That happens about 2.5 hours prior to launch. It's when it starts. And then if all has gone well and we have a good range and good weather, we'll be set to go starting at 4:05 for RT0. All right, now I want to turn it over to my good friend, Scott Messer from United Launch Alliance. Scott?
Thank you, Tim. On behalf of United Launch Alliance, I want to welcome you to the InSight launch. We at United Launch Alliance are super excited. Maybe not as excited as Tim, but we are super excited to be part of this critical launch. United Launch Alliance, we've launched 5 times so far this year, and we're expecting Saturday morning's launch to be the 128th consecutive successful launch from United Launch Alliance. So this is a great vehicle, as Tim has mentioned, that is out there. It is the 401. We have several different configurations. The Atlas 401 has a 4-meter fairing up here at the top to house the spacecraft and protect it until we get out of the atmosphere. And it's got a 4-meter body, and it doesn't have any solid rocket motors on it. But so the United Launch Alliance, out of the 128 launches that we've had in our history, 37 of those have been with the 401. So this is by far the workhorse of our Atlas family. Almost half of our Atlas vehicles have launched this configuration, which is very, very, has been a very good vehicle for us and for our customers. So one of the questions that keeps coming up, you might have heard this is the first planetary launch from the West Coast. And a lot of people keep asking, well, why is that? And just in simple terms, NASA sent us a proposal a while back to launch in 2016. We went and looked at our manifest out on the East Coast. It was a little crowded, and we felt like getting a vehicle out here would be a great idea, get out of that congestion of the manifest. Because this spacecraft was originally sized for a Delta II, and we were going to propose and launch on an Atlas 401, we had plenty of performance to do that. So we decided to go ahead and propose that. NASA liked it, and everybody's excited about it. So it's really an exciting thing. So we got a short video here that'll show you what's going to happen tomorrow morning, or I'm sorry, Saturday morning. So if we could roll that video and show what's going to go happen.
We have ignition of the RD-180 main engine. 1. Liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine ignites and generates more than 860,000 pounds of thrust to lift the rocket away from the pad. The Atlas V reaches Mach 1, the speed of sound, at 1 minute 17 seconds. At 4 minutes 4 seconds, propellant levels deplete and the main engine shuts down. 6 seconds later, the Atlas Centaur separation system activates to release the booster stage. The vehicle now weighs a little more than 7% of what it did at liftoff. At 4 minutes 20 seconds, the first Centaur main engine burn begins. At approximately 4 minutes 28 seconds, the payload fairing is jettisoned. At 13 minutes 16 seconds, cutoff of the Centaur main engine, or MECO-1, occurs. At nearly 1 hour and 15 minutes, the Centaur main engine is restarted for the second and final burn. Approximately 4 minutes and 49 seconds later, final cutoff of the Centaur main engine occurs. At 1 hour, 28 minutes, and 40 seconds, Centaur releases NASA's InSight spacecraft on its journey to Mars. Marco A separates 1 hour, 29 minutes into flight, followed 48 seconds later by the separation of Marco B.
So it was mentioned earlier that there have been a lot of missions to Mars, and by our count, all of the missions that have gone to Mars since 1960 have launched on a ULA or heritage vehicle. So we are very proud of our history with the Mars program. And as I mentioned earlier, 100% of our missions have been successful in the last 10 years, and so we are thrilled to be a part of this and offer that again to our customers. We are very proud. We want to say thank you to all of our mission partners, to NASA, to Lockheed Martin, to JPL, everyone for letting us be part of this wonderful and exciting mission. And in conclusion, I'll just say, go Atlas, go InSight.
All right. Absolutely. Okay, I understand that we do have some social media questions, some Ask NASA questions. So if we can get a microphone down front here to Jason Townsend from the NASA headquarters social media team. Again, you can submit those online with the hashtag AskNASA, and those that we can't get to during the show today, we'll be answering more online later and also in launch commentary. Jason?
All right, first question here comes from Twitter user Tracy, who's asking, how much does NASA coordinate with the United States Air Force, and can you talk about that a little bit?
I will take that one. We coordinate with our partners in the Air Force a lot. We have a terrific partnership on both ranges. Here we are at the 30th Space Wing, incredible hosts. Vandenberg Air Force Base is a wonderful place. I have, when working a mission at Vandenberg, probably at least weekly normally multiple weekly contact. You're going to hear from the wing commander here at the 30th Space Wing, Colonel Huff, in just a little bit. His team is amazing. The level of support they provide for both Air Force missions, obviously, but for other missions, for the science missions, and for commercial missions as well. So there is a tremendous amount of coordination at my level, at NASA headquarters level, to Air Force Pentagon level, Air Force higher headquarters level. So it's a great partnership.
Wonderful. A couple of folks are asking here a variety of these sorts of questions here. What factors are determining the launch going from California instead of Florida, and why aren't launches from the West Coast to the planets as common as launches from the East Coast?
So I can take that. So when NASA puts out a request for a proposal, we make an effort to match the vehicle to the performance of the required of the spacecraft. As I mentioned earlier, the InSight spacecraft is a little smaller and easily fits into our Atlas 401. So one of the reasons why we traditionally have launched interplanetary missions from the East Coast is because when we do that, we get to take advantage of the rotation of the Earth. And so it's like jumping off of a rotating disk going in the direction that the disk is going. So you get a little extra speed off it, and it makes it a little easier. You don't have to have quite as large a vehicle or quite as much power in your vehicle. In this case, because the Atlas 401 had enough performance, we were able to do that off the West Coast, where we'll go kind of the opposite direction. Initially, we'll jump off the world going the opposite direction it spins, if you will, and head south more, and so we don't get to take as much advantage of the rotation of the Earth. So that's why we're doing InSight here, because we have the performance, and why we normally would do things off of the East Coast.
Fantastic. Do we have any other questions here in the room on the media side? Right. Yeah, we do have a social media question down here in the front. Let's wait for a microphone, if we can get up here with one of those for you, so that everyone listening to the broadcast can hear you, and we can also hear you in the room.
Hi, I'm Mike 3J Raman. I'm a public defender from Philadelphia. So I saw that Marco A and Marco B will be launching with the InSight. Can you tell us a little bit about the Marco cubes and what they add to the InSight mission?
Actually, we're going to have a little segment about Marco, so why don't we hang on to that one for when we go to Q&A then. Any other questions on this side or in any part of the house? One to my right. Okay. Shannon's coming to you with the mic.
Hi. So is there, if the InSight mission, if the window gets pushed, or if the launch goes beyond the mission window, is there the possibility to put InSight onto another rocket and potentially launch from the East Coast, or even here?
Not until 26 months from now. So that would be if we are not able to launch for some really bad reason. We got 35 opportunities between Saturday and June 8th. That's a lot of chances to launch. But in a really bad situation, we'd have to wait for that next Mars window.
Yeah, and if I would just add, the Atlas performance would indicate that we've got about a 95, 98% probability of getting off in the next 2 days.
Okay, and I think we've got one more question right down here. Yes, move in. Redundant systems. This is what NASA's good at.
Hi, my name is Fig O'Reilly, and I'm with Girls Who Code. My question is, will the data received be published openly?
So the science data from InSight, so I'm going to turn that back over to one of my science, but most of this data is going to eventually wind up in the public domain, Bruce?
All of the science data from NASA missions ends up in the public domain. I've signed basically a document saying that I do solemnly swear that all of our data will be on the internet in the Planetary Data System repository in less than 6 months after we acquire it. And our goal is to actually, once we get the mission rolling and we got our data pipeline all worked out, is actually to push out our science data, our seismic data, within a matter of weeks of acquisition, and the images we get from here, we hope to get on the internet within days of acquisition. So yes, the data that's coming down from InSight belongs to everybody. It belongs to the taxpayers in the United States. It belongs to the taxpayers in Europe. It really belongs to the whole world, and we're going to push it out just as fast as we can.
All right, that's right. All these data are yours. And with that, thank you so much to Tim and Scott. Big round of applause for them. And a lot of talk there about the Air Force. We would not be lifting off this planet if it weren't for the 30th Space Wing here at Vandenberg Air Force Base. So let's go ahead and bring up two members of the 30th Space Wing. Someone possibly with the coolest title in this entire roster, and that is a high bar, sir. Colonel Michael Huff, the Space Launch Commander of the 30th Space Wing, and he is joined by First Lieutenant Christina Williams, the Weather Officer. Thank you.
Can you hear me? Check. Okay. Well, one, I appreciate you getting my name right. That's not an easy name. So H-O-U-G-H, I usually get ho, hu, how, so thanks for that. So Colonel Mike Huff, commander of the 30th Space Wing. I've been in the seat now for just close to a year. And, you've heard the term excitement, and of course that's exactly what we feel in supporting this launch. I tell you what, launches don't get old. They are fantastic, and I hate to I'm going to be inside on this launch. I am going to be the sitting on console for it. And I hate that I won't actually be able to see it, live. And I tell you too, and because the Lieutenant Williams is going to catch this one here in a second, I'm glad you were able to see the visual of the launch on the screen, because anybody who's been to Central Coast, California for a while knows we get a pretty good marine layer. So at least you could say you saw a launch today by looking at that video. But I think we're going to have some marine layer coming out.
Yes, sir.
Okay, and then so our mission here is we help support we help support these launches. Of course, we rely on the experts that you heard from United Launch Alliance, of course from NASA, and many other launch providers here on the Western Range. But our role here, my role, is to operate this thing called the Western Range. And what I liken it to is that we have these launch providers come in, and I quote unquote they plug in. So we provide them the infrastructure, the power, the communications, and then the telemetry and the radar and the optics to be able to launch that and support that launch. We also provide, we're responsible for public safety and security as well. So not only do I have, just a fantastic team of airmen out there who are, doing the groundwork to make that connection with the communications and the power and all that, but also have defenders, my security forces, who are out there and they sweep the area again and just keep it safe and secure. So it's a little bit about me. How about over to you, LT?
All right, thank you, sir. It's crazy to think that some people in here have been working on this launch for 7 years, because I've only been working on it for 2 months now. But I am First Lieutenant Christina Williams, and I am the Launch Weather Officer for the mission. So a little bit about myself. I'm originally from Wisconsin. I have a degree in meteorology from the University of Wisconsin-Madison. I've been in the Air Force for about 3.5 years now, and I've been at Vandenberg for about 5 months. So as a Launch Weather Officer, or an LWO as we like to call it, my job will be to lead an 11-member launch weather team. We provide pre-launch support with our forecast leading up to the launch, as well as support on day of launch. As the leader, we operate out of 4 locations on day of launch. So I will be working in the Western Range Operation Control Center, which is where the main weather hub on day of launch. I will also have my range weather forecasters will be working out of our weather station, which is where we typically do our day-to-day weather operations when we are not in a launch or working on a launch. I will also have my balloon editors and contractors releasing balloons and editing the data in our balloon shop. And we will have forward observers at a site about a mile away from the launch pad taking observations. 3 days leading forecast. This morning I sent our L-2 day forecast. Tomorrow I will be sending out our L-1 day forecast. On these forecasts, we give a brief overview of what type of weather we are expecting, specifically for liftoff, or T0. And we also include probabilities of violation, or POVs, for both range safety and user constraints. And what these are the likelihood that a certain constraint will be violated or exceeded. So keep that in mind for later in the briefing. So if we take a look at the current satellite, currently we're seeing a ridge building in with an upper level trough well to the west of the region, which will be moving slowly towards us. There is some shallow marine layer fog out off the coast of California, and as I'm sure you saw this morning, there was some fog over land as well. So looking at our launch day forecast, we're expecting winds out of the north at 7 to 10 knots with temperatures in the low 50s. Visibility is expected to be 1/2 to 1 statute mile due to fog, as we are expecting that shallow marine layer fog to impact the pad at T0. For an overall probability of violation, or POV, we're expecting 80% due to the required range safety launch visibility constraint. All other mandatory range safety and launch agency constraints have a POV of 0%. So for our scrub day forecast, we are expecting to see high pressure moving out as the upper level trough makes its way towards us. However, it will not affect the weather here too much. Winds will shift to be out of the northwest, increasing slightly to 8 to 12 knots. Temperature still in the low 50s with visibility 3/4 to 1.5 miles. So slightly improved, but still not great. So still assigning that 80% probability of violation due to the range safety required launch visibility constraint. So I know 80%, ooh, that's a big number, right? It does not necessarily mean that we won't launch because of weather. So what it is we, like I said, you probably saw this morning, there is fog that happens along the coast. It's a common event here, especially this time of year. ULA and NASA are both aware of it, and they are prepared to launch through it. The constraint is for safety, but they do have ways of mitigating it. So essentially, by assigning 80%, I'm saying there is an 80% chance you will not be able to see the rocket launch at liftoff. So this is all I have for weather.
Which is why I'm glad you saw that video.
So before you crush all my dreams, I'm still going to hear it, and I'm going to feel it. I'm going to feel it in my bones, right?
Indeed. Oh, yeah.
Absolutely.
And where we're going to be sitting, even though we're going to be indoors, further away than, a lot of the folks looking at it will also feel it as well inside. And that's a great thing. So.
Fantastic. Okay, so do we have any questions for our friends from the Air Force? Can we get a mic on this side?
Hey there, Tyler Pratt, KCBX, Central Coast Public Radio. Since this is an historic mission from the West Coast, can you spend a minute talking about sort of the economic impact to the Central Coast, and maybe did this bring in a lot of jobs?
So I won't speak to the economic impact overall. I mean, obviously you can see by the, this is the first time, by the way, that I've stood up in front of a crowd and talked about a mission. So you can see that this one has a little bit more importance than what we've done in the past. Our first interplanetary launch from Vandenberg Air Force Base. Again, to me, a launch is a launch is a launch. I don't mean to be too flippant about it. I care, it gets off the ground. But because this one is so historic, like you said, that it's just garnered a lot of attention. And I think from that standpoint, there are a lot of people that are coming in and viewing the launch. But I don't have an answer for you, as far as long term. This particular one, I would have to have some of our partners answer that question. From an Air Force standpoint, I don't track that from a military standpoint.
Okay, we're going to go to a reporter question on the phone line. Aviation Week, go ahead.
Hi, thanks very much. I'm a little confused by the launch violation forecast. Are you saying, do you have a number for the probability of flying based on other factors, not including whether people on the ground will be able to see it or not?
So if you're talking about visibility itself, we are anticipating visibility to be bad that day. I'm expecting it to be 1/2 to 1 statute mile. So with that being said, the probability of violation for that specific constraint is at 80%. So there's an 80% chance that we will have visibility down that low and you will not be able to see the launch. However, for the launch to actually happen, we are anticipating for all other mandatory range safety and user constraints that the probability of violation is 0%. And as I said, safety has the ability to mitigate that one constraint involving visibility. So if they choose to do so, we may be able to not have to even monitor that constraint during the launch, in which case, yes, you will not be able to see the launch, but the launch could still be successful and not be impacted by weather.
Okay, I think we've got another question on this side of the house. Elena, if we can get a microphone. Thank you.
Randy Page of CBS 2 News in Los Angeles. Just a point of clarification. So we know that there's a good chance we won't see the launch anywhere around the launch pad. The question, though, for people throughout Southern California, when it gets to the higher elevations, will it be seen?
Yes. So we are anticipating this fog to be very shallow, so only about 200 to 600 feet above the pad. So as soon as it breaches above that, then if you're standing far enough away or in a distance, you should be able to see the rocket.
You would recommend for people to get up at 4 o'clock in the morning, it might be worth seeing, right?
If you stand above 600 feet, then yes.
Thank you.
All right, we've got another question right down here in front.
Hi, Stephen Clark from Spaceflight Now. Just another clarification on the visibility. What are some of the mitigations, if one of you can speak about that from a safety perspective to waive that constraint for visibility?
So we look to our launch partner, and so we have a lot of things that monitor the rocket, okay? And if one of those things should fail, and that we have to have visibility for a safety standpoint, then the Air Force would say, yes, now we have to have visibility, and now you would have an 80% chance of violating. So as you heard the lieutenant talk about, that there's nothing else getting in the way of this launch. So we are clean from that standpoint. Now, if ULA or if NASA came to us and said, hey, we absolutely have to have visibility on this launch, then of course we would abide, we'd listen to them and say, gotcha, and then we'd be at that point of 80%. But there's nothing standing in the way of that right now.
Fantastic. All right, a big round of applause for our friends from the 30th Space Wing. So as you saw in that ULA video earlier in the show, InSight is not the only spacecraft that's set to launch on May 5th. There are 2 small sats, Mars Cube 1 or MARCO. Go ahead and come on up here, guys, because we've got a very lovely another full-scale model, believe it or not. We've got our InSight lander, and then we've got Mars Cube 1, MARCO. This is a tech demo. Small size does not belie its big goals. So let's go ahead and bring this out.
So as they bring that out, my name is Ann Marinin. I am a systems engineer at JPL working on the MARCO mission. This is a full-sized replica of the MARCO spacecraft. As you can see, is significantly smaller than InSight. This is a CubeSat, and more specifically a 6U CubeSat. A U is a 10 by 10 by 10 centimeter cube. And each one of these satellites weighs about 30 pounds, but when it's all folded up, it's about the size of a family-sized cereal box. The MARCO is primarily a technology demonstration. This is the first opportunity for a CubeSat with this technology to fly on an interplanetary trajectory. There are 3 main technologies that MARCO will be demonstrating. One is a propulsion system on board for MARCO to do its own trajectory correction maneuvers. The propellant on board is the same liquid that you would find inside a fire extinguisher. And for that reason, for those of you who have seen the movie WALL-E, the main character flies around space using a fire extinguisher. We've nicknamed the 2 MARCO spacecraft WALL-E and EVA. Their official names are MARCO A and B. But the other 2 main technologies that are being demonstrated were developed specifically in-house at JPL to fly on this mission are One is a radio about the size of a softball, and it was designed specifically to fit in a CubeSat form factor, but also to be able to interface with the Deep Space Network. You can't see it inside here, but that is a big deal because in interplanetary space, communications is a challenge that CubeSats have not had to deal with before. The satellites are much farther away from Earth, and so they have to figure out how to range and determine the orbit of the CubeSat, and so that radio enables this mission to do that. The high gain antenna, is another technology that was developed at JPL. It's called a passive phased array, and you can see the circular pattern on here. When the radio sends a signal and it illuminates this panel, the signal is focused just like it was coming out of a parabolic dish. But because it is flat like this, it can stow in a very small volume, which is ideal for launching a CubeSat in a box. Some other main deployables you see here, there's solar panels. These deploy at the beginning of the mission. It generates about 40 watts at Earth, only about 17 watts near Mars. And then there's an antenna on the bottom. If Marco is successful, as I mentioned, it is a technology demonstration. There's a lot of new things happening with it, but it is on a flyby trajectory to Mars. So as it flies by, if everything goes well and it's timed perfectly, this antenna is designed to receive signals from InSight as InSight goes through its entry, descent, and landing phase. The radio does some digitization on board and then transmits that back directly to Earth over X-band with this antenna. I'm going to turn it over to Andy to talk more about the Marco mission and the CubeSat paradigm in general.
Thank you very much. Now, Marco is the first CubeSat to head out to interplanetary space. I should say the two Marco spacecraft are the first two to head out there. Yet they build upon almost 20 years of CubeSat experience in low Earth orbit. These CubeSat missions around the Earth have performed educational missions, technological, commercial, and scientific ones, and they grow in capability each and every year, with almost 700 CubeSats flying around the Earth. Now, these CubeSats are flying about 800 kilometers above the surface, and yet with Marco, we're sending our two spacecraft approximately 158 million kilometers away from Earth. This is a significant distance, and it's why this is a technology demonstration mission, because of all the things that need to go right along the way. As Annie mentioned, we need to be able to communicate, to navigate, to be able to maneuver in the deep space environment there away from Earth and dealing with light time delay and all of the other issues we have in the deep space environment. On Saturday, we'll be launching with the InSight mission, and approximately 90 minutes after launch, once InSight separates from that upper stage, the two Marco spacecraft will also pop up to the side. I have a short video to show you that will explain some of the details of early launch. Marco A will pop out first from the aft bulkhead carrier of the Centaur upper stage, and from that side it will slowly drift off. The Centaur will rotate 180 degrees and then deploy the Marco B spacecraft. Each of these will be flying out towards Mars independent from InSight itself over the following 6.5 months. In the early minutes of the mission itself, we'll start to deploy our solar panels, which you can see out on the table in front of us and on the screen. The solar panels will deploy off on the right-hand side, followed by a burn to deploy them on the left-hand side of the spacecraft. And these solar panels are critical for recharging the batteries, as our spacecraft have been powered off since late February. After the solar panels are deployed, we'll begin our checkout operations and deployment of all the antennas you see before you. The high-gain array will pop out first over the next couple of days, followed soon by the UHF antenna, which comes out the bottom side of the spacecraft. Each of these are critical not only to provide us communication as we're going away from Earth, but once we get near Mars, to be able to support the InSight primary spacecraft mission. InSight will broadcast UHF telemetry up to the Marco spacecraft, which will relay them out the high-gain antenna and send that data down to Madrid's 70-meter dish. Now, we do not need to wait to Mars to actually test out this relay system. We'll be working with Morehead State University and others to actually do a relay as we're closer to Earth to check out the system along the way. The Marco spacecraft are really a collaboration, not only from NASA JPL, NASA headquarters, but many other commercial and university academic entities that are out there in order to pull this together. It is really a collaboration of the entire CubeSat community and a building upon all of the effort that has been done over the last 20 years that allows us to take the first CubeSats out to deep space. And we're very much looking forward to riding along with InSight. Stephanie, we have a few questions.
Yeah, so I was so excited getting your full-scale model out here and getting you guys on stage that I failed to mention. This is Andy Clash, the Marco Chief Engineer from NASA's Jet Propulsion Laboratory. So does anybody have any questions for Annie or Andy? CubeSat questions? Yes, right down here in front. Let's go ahead and get you a microphone. Shannon, come on down. You're the next mic runner on this show. Right here to Athena in the front row.
Hi, my name is Athena Brunsberger. I'm here with Astro Athens. I'm wondering, foreseeing the future with humans essentially one day colonizing Mars, do you see this type of technology for satellites being able to be used to communicate to those living on Mars for their technology, since this is able to pick up signals for the InSight mission?
Our particular spacecraft here are really just demonstrating what we might be able to use in the future. Small spacecraft, now spacecraft overall, are very good at focused missions. They can do one thing, they can do that one thing very, very well on here. So we're excited to see how the capability may grow in the future, but everything that we have that is so small usually just does one thing very well.
Okay, and we've got another question there, and then we'll take a couple of Ask NASA questions.
This is such an exciting new technology. What's the next step after this mission for this technology, if it's successful?
Yeah, so there are actually, on SLS EM1, so the first launch of the Space Launch System, there are 13 CubeSats of this size that are manifest on that launch. About half of them are using the same radio technology that is being developed, that is flying on Marco. And I'm working on at least one of them. But yeah, so this technology, even before it flies, it's being used by future missions.
Okay, Jason?
All right. So coming in on Ask NASA here, there's a question from Twitter user Roland who's asking, will the Marcos be utilized or monitored at all after they've completed their flyby of Mars?
Soon after the flyby of Mars, each of the Marco spacecraft will actually attempt to rebroadcast the same InSight data back down to Earth. Within the first couple of weeks past the Mars flyby on there, we'll be checking out the last state of the health for the Marco spacecraft, and then that will be the end of the primary mission for the Marcos.
Okay, and we had one go back. Remember, we had our Marco question earlier in the show. I want to make sure that we get it in now. Oh, all right. Well, then, any other questions? Any other questions for Marco, small sats? All right, we got one in the back there.
Could you talk a little about how Marco orients itself using constellations?
So Marco, like many different spacecraft out there, uses stars and a star tracker on board, a small telescope to look at the stars, identify how it's oriented with respect to those stars, and then pass that on to the broader spacecraft there. Once we have the knowledge of how we're pointed, we use small reaction wheels, small spinning wheels on board, along with this cold gas system that Annie described, in order to actually turn ourselves to where we'd like to be oriented along the way.
All right, and with that, thank you, Marco team. So I know we had more Ask NASA questions than we got to during the show. We will be answering some of those online on the various networks that they came in on after the show, and also we'll be referring some of them to the subject matter experts in launch commentary. You can interact with the mission directly online on social media. So just go to the handle @NASA InSight on both Facebook and Twitter, and you can continue to get your questions answered through launch, through cruise, landing, and surface operations. If you want to find out more, please visit the mission online at mars.nasa.gov/insight or nasa.gov/insight. The launch window for InSight opens Saturday, May 5th. We will be back here live on NASA TV and all the online simulcasts starting at 3:30 a.m. Pacific Daylight Time, with that launch expected no earlier than 4:05 a.m. PDT. All right, with that, we'll see you online. Go NASA, go InSight. Thank you.